Now that we've taken a look at how exponential functions work and some other applications, this video is going to focus on the graphs of exponential functions. There is some key information that we will look for in the graph of our exponential functions. Now, the general shape of an exponential function is it's going to start off really flat, close to zero, and then it's going to bend up and get big really fast. Or sometimes it'll start the other way. That's exponential growth. If we have exponential decay, it's going to start off really big until it bends and levels off at zero, but it's never going to get to zero. Either way you look at it, the function is going to be of the form f of x equals ab to the x. The a is that starting initial value, so that'll always be the point on the graph 0, comma a on both graphs. And then there'll always be a second point on the graph at 1, comma ab. And if it's growing, ab is going to be a bigger number, and if it's shrinking, AB is going to be a decimal or a fraction, depending on if it's growth or decays. So growth looks like the first graph, decay, it looks at the second graph. Either way, that's going to be the general shape of the graph. Now, the important thing on here, and you can kind of see it on this graph, is B determines the growth rate. In this first graph on the left, the b is going to be greater than 1. If b is greater than 1, what that means is the graph is increasing. Whereas x goes to negative infinity on the left side, we see the graph levels out at 0, f of x goes to 0 for its long-term behavior. But if x goes to positive infinity, the graph on the right side is heading off to positive infinity. Contrast that with the second graph I have on here with the decay. The b is going to be less than 1. It's going to be a fraction or a decimal. If b is less than 1, then we have the case where the graph is decreasing. And for long-term behavior on the left, we see now on the left it's going to positive infinity. So as x goes to the left, negative infinity, long-term behavior as the overall graph goes to positive infinity. But as x goes to positive infinity off the right, the graph is leveling off at a height of 0. So this is that essential information we need to know about this graph, f of x equals ab to the x. Using this information, we should be able to draw some graphs. Let's graph f of x equals 3 times 1/2 to the x. Now we know the graph is going to level off at 0, so I'm going to draw a dotted line that represents the asymptote of the graph leveling off at 0. We also know 3 is the a and 1/2 is the b. And there's always a point at 0, comma, whatever the a is. So we know 0, comma 3 is going to be on this graph. So I'll go 0, 1, 2, 3 and make my first point. I also know another key point is when I plug 1 in, we get whatever a times b is. 3 times 1/2 is 3/2. So at 1, comma 3/2, or 1.5, I've got another point. I also know because the b is less than 1, it's going to be a decay situation where it's shrinking down and leveling off to 0. And so this is my graph then of 3 times 1/2 to the x. Let's try another example. Let's graph f of x equals 2 times 3 to the x. Again, I should be able to look at this and see that 2 is my a, 3 is my b. And there's always a point at 0, comma a, in this case 0, comma 2, and a point at 1, comma, AB. 2 times 3 is 6. So now when I look at my graph, again, I'm going to draw an asymptote at 0, so I know the graph is going to level off. It's never going to cross 0. But I've got a point at 0, 2, and 1, 6. I also know because the b is bigger than 1, this is an increasing situation. So the graph does increase with the long-term behavior of going to infinity on the right. So with this in mind, we should be able to predict the graphs of lots of different equations. But I want to also bring in something we saw from chapter 1, and that's transformations of our graphs. We can transform this graph just like we transformed other graphs back in chapter 1. So if we've got f of x equals a times b to the x minus h plus k, what we see is the x minus h moves h units to the right, and the k moves k units up. These exponential functions have an interesting result, though, if we adjust for some exponent properties. If we've got that b raised to an exponent, we can split that exponent up into b to the x and b to the negative h plus k. And that's just the exponent property that says we can break up a sum of exponents into two common bases. Next, I can use the commutative property of multiplication to put the b to the negative h first times b to the x plus k. Then we can group the a and the b to the negative h. Because there's no variables in there, that's going to be some constant number. They can group together. I'm going to call that the capital A times b to the x plus k. And so this becomes our new transformation equation that simply just transforms k units up. We actually don't ever have to worry about left and right transformations. We just have to go up and down because everything else gets absorbed into that a out front. So for example, if I wanted to graph f of x equals 2 times 3 to the x minus 3. Let's see what we can do with this. Now, we know originally before the minus 3, there would have been an asymptote at 0 where it levels off and never crosses. We would have known it goes through 0, 2 and 1, 6. And so before the minus 3, the graph would have looked like this. Now, the minus 3 is going to move everything down 3. So the first thing I would do is I'm going to move that asymptote down 3, down to negative 3. So that's where it's going to level off now. Then I've got my point at 0. I'm going to move it down 3. And then I've got my dot at 6. I'm going to move it down 3. 1, 2, 3. And what I'm going to end up with is this new graph that's just been shifted down 3. In fact, I can erase the blue graph because I don't really need it. The green graph is the one I want. We've shifted that graph down 3. It helped us to first graph the original parent function and then do the minus 3, but all we have to do is worry about vertical shifts with exponentials. Let's see if we can go the other way. Let's start with the graph and see if we can build an equation. Let's put a point at 0, 1. Let's put a point at negative 2, negative 3. And let's let the whole thing level off. It's never going to cross an asymptote here at negative 4. So here is my graph. And we want the equation here. The easiest thing to see is the vertical shift is down 4 because that asymptote, that level off point, has gone down 4. So if I think about the general form of my function, it's a times b to the x with a minus 4 at the end. The next nice thing to use to help me build my equation, as we look for what a and b are, is I always try and use the point at 0, because nice things happen at 0. Here we have 0, 1, which means the answer is 1 when x is 0. Anything to the 0 power becomes 1, and so we can kind of ignore that part, and we have 1 equals a minus 4. Add 4 to both sides, and 5 is equal to a. So now we know that f of x is equal to 5 times b to the x minus 4. We're getting closer to finding our actual function. Well, now we have this other point at -2, -3. So if we plug -3 in for the answer, and -2 in for the x, we can try and solve what we end up with. Add 4 to both sides. 1 equals 5 times b to the -2. Divide both sides by 5. b to the -2 equals 1/5. And then a negative exponent just flips everything over. So if I flip 1/5, I get 5 equals b squared. Take the square root of both sides. And b is equal to approximately 2.236. Put that all together in the equation for our graph. The function is f of x equals a, which we found out to be 5, times b, which we found out to be 2.236, raised to the x, and then the vertical shift of -4, and we've got our function. Now, vertical shifts aren't the only transformation that we saw from Chapter 1. Also in Chapter 1, we saw reflections. And that was done by making either the whole function negative or just the x negative. And so we've kind of got 4 options. We've got f of x equals a times b to the x. And if the b is bigger than 1, it's going to have the shape of this, leveling off at 0 and then taking off to infinity. This graph we know has a point at 0, a, and another point at 1, ab. But if I went in and made the whole thing negative, in this case, we're going to have a reflection over the x-axis, which means the graph is going to start off on the bottom flat and then go down. It's still going to have a point at 0, but now it's a, and the next point is at 1, ab. Third option is if we just make the x part negative. If we have f of x equals ab to the -x, now what we're going to see is a reflection across the y-axis. It's almost going to look like a graph where the b is less than 1. In this case, it's going to come down from infinity and level off at 0. We're still going to have a point at 0, a, but now the second key point is on the other side. It's at -1, ab. Or we could do both and see both together, where we've got f of x is equal to -ab to the -x. And if we're doing both, then what we'll have is a reflection across the x and the y-axis, which means it's going to look something like this, where we've still got the point now at 0, a, and the second point is at -1, ab. Let's take a look at an example that combines all of this together. We're going to have to figure out how to draw the shape of the exponential, and there's going to be a vertical shift, and there's going to be a reflection. Here is the graph we're going to find the equation of. First, I'm going to draw a horizontal asymptote at 5. And that's where the graph is going to get closer to and never cross. Then I'm going to put a point at 0, 2. And I'm going to put a point at -1, 3. And I'm going to put a point at 2, -2. So I can kind of connect the dots. And we get this graph here. Now I can see by the way it's flipped, it's going down instead of up. I'm going to assume this means the A is going to be negative. But we can build this in much the same way that we built the prior examples. First, I see that the asymptote where it levels off has gone up 5 units. So now I know the function is something like a times b to the x plus 5. Next, I like to use the point at 0 to figure out what a is. So 0, 2 means the answer is 2 times a b to the 0 plus 5. But b to the 0 just becomes 1, so we really have 2 equals a plus 5. Subtract 5 from both sides, and -3 equals a. Just like we expected, because it's going down away from the asymptote, the a is negative, times -3 times b to the x plus 5. We still need to figure out what the b is. We can pick either of the other points. I'm going to pick the -1, 3. So if we have 3 for an answer, equals -3 b to the -1 plus 5. If I subtract 5 from both sides, -2 equals -3 b to the -1. Divide both sides by -3. And b to the -1 equals, a negative divided by a negative is a positive 2/3. And I know a negative exponent means flip the fraction. So b is 3/2. Put it all together. My original function with a and b filled in, f of x equals a, which we now know is -3, times b, 3/2, to the x plus 5. And now we've got the equation for the graph of our transformed reflected exponential. All right, it's your turn to practice with some of these. Good luck on the assignment, and we'll see you in the next video.